Hello, in this video I'm going to talk to you about the angle between vectors and how it calculates it. And incidentally, I'm going to end up talking to you about a scalar product. So think this one out. Now you have two vectors, vector A and vector B, and you know the magnitudes of the two vectors, right? You know the modulus. Remember, we did that with a bit of Pythagoras. So we have points A and B, right? And the position vectors of those are vector A and vector B. That's how to go from the origin to the point. And the magnitude, of course, of the vector that goes from A to B. That's what I'm going to have because I got this, right? So what do I have? Basically, what I have is a triangle, right? I have point A over here, and I know this distance. I have vector B over here, and I know this distance, and I also know this distance here. So, remember a bit of trigonometry, I can calculate this angle. Bit of cosine rule, you should be able to do it. So ultimately, if you know two vectors, we can draw a triangle of which we know the length of the three sides, so we can use the cosine rule to calculate this angle here. You could simply do trigonometry, but there's something that's going to make your life a bit easier here. You can throw it in, etc. You calculate everything, but ultimately you end up with this. This is what you would end up if you do use cosine rule, a lot of calculation here and there, because you have AB over here, so you have to calculate AB using vector A and vector B, and it will be kind of messy. If you want, give it a shot, but ultimately this is what gives you the cosine of the angle, this whole expression here. So what happens is that we're going to define one of the elements you've just seen in that equation as the scalar product. Which one? This one here, because this thing here is going to turn out to be extremely useful. So we call it the scalar product or the dot product, and ultimately what is it that we're doing? We take two vectors, we multiply them, and you end up multiplying its coefficients. So the x coefficient of A times the x coefficient of B plus the y coefficient of A times the y coefficient of B, and so on. But ultimately, because I can take this part of the equation and take it over here, it means that this thing is the same thing as this thing. So I can write the scalar product both like this and like this. So this is going to be useful because I know that if they're perpendicular, if two vectors are perpendicular, well then the cosine of that angle, the angle that they're going to form, is going to be the cosine of 90, and that's going to be 0, right? So the scalar product has to give me 0. So at any point, if I have two vectors, all I have to do to figure out whether they're perpendicular or not is to do the scalar product. Remember, x coordinate of A times x coordinate of B plus y coordinate of A times y coordinate of B, and so on. And if it gives them 0, I know that they are perpendicular, or what also means normal vectors. And if they're parallel, well, simply multiplying them is going to be the same thing as multiplying their modulus. So here's a typical exercise. I'm going to do it in two-dimensional vectors. I can calculate the angle between vector A and vector B. How do I do that? Again, I use the scalar product. I have this formula here available in your formula booklet. So what is it going to mean? It's going to mean that 1 times minus 1 plus 3 times 2. And down here, the modulus of A, which is square root of 1 squared plus 3 squared, divided by the modulus of B, which is square root of minus 1 squared plus 2 squared. So I end up with 5 divided by 5 square root of 2, which means the angle they form is 45 degrees. I do the same thing with B and C, and I can get that it's approximately 117 degrees rounded to three significant figures. And it makes sense, because if I represent them, this is what they look like. So it makes sense that the angle between A and B, this angle here, that could be 45 more or less. And the angle between B and C, this angle here, that's about 117 degrees. So that's basically what the scalar product does. Here's another example with three-dimensional vectors. Again, we can just look for the angle between A and B, but now we're going to have to use the bigger extended version of the formula. I can get that the angle here would be 73.22, 90 degrees for B and C, because remember it gives me 0, meaning that B and C are perpendicular. And if I do it for A and D, I'm going to get again 1. I get 1 exactly. And what does that mean? Well, if I get 1 exactly, the cosine of something being 1 means that that angle has to be 0. So that means that A and D are actually parallel vectors, which I can check because I know how to do that. Because you see, like 1/2 divided by 1, it gives me 1/2, minus 1/2 divided by minus 1, again, it gives me 1/2, and 1 divided by 2, of course, gives me 1/2. So yes, A and D are parallel. I checked with my other method, but again, you calculate the angle, gives me 0, which obviously means that they are parallel. So that's again the scalar product for you.